I want to summarize how the one-dimensional discussion I gave yesterday about the Fourier transform and Poisson summation looks in higher dimensions in Euclidean space. So, so let's say, I'll make a table of the one-dimensional case and the k-dimensional case. So, so if we have, so for instance, for the Fourier transform, so if we have a function going from R to C that's, say, decay sufficiently rapidly, its Fourier transform also goes from R to C, and the Fourier transform at Y, as you integrate on R, f of x against e to the minus 2 pi I xy with respect to x. So the new variable y in the Fourier transform only shows up on the right side in the exponent. Everything else is the original variable x. Okay. And likewise for the higher dimensional case, if you have a function from Rk to C, its Fourier transform also is defined from Rk to C, and its value on a vector y, as you integrate over R to the k, f of x, x means x1 through xk, and then you're going to multiply by e to the minus 2 pi I times the dot product, x dot y. So in the one-dimensional case, it's just a simple product. Okay, so it generalizes, if you use the dot product notation, it generalizes in a very natural way. And the Poisson summation formula looks the same in both settings. Whoops. We're going to have to do some actual calculations to give some examples. But the Poisson summation formula in one dimension, if I sum over all integers of a function for which I can talk about the Fourier transform, and these series are converge, so everything makes sense. If you sum a function and its Fourier transform over the integers, you're going to get the same value. And in higher dimensions, if you sum, let's use v for our vector variable in zk, f of v, it's the same as the Fourier transform on z to the k. So it looks exactly the same. Now we want to present some examples of this. So if we took in one dimension, the important case for us is e to the minus pi x squared, or maybe more generally e to the minus pi x squared t, where t is positive. Okay, we were working with that yesterday. And so in this case, the Fourier transform is itself. Or if you insert a scaling factor, you're going to get 1 over root t times e to the minus pi y squared over t. So the t changes in two ways. In the Fourier transform, in the second example, you get a 1 over the square root on the outside, and you get a 1 over t in the exponent. And if here I took f of x to be e to the minus pi x dot x, or e to the minus pi x dot x times a positive scaling factor, then maybe I should make a dividing line here. Then the Fourier transform, in the first case, it's the same. It's e to the minus pi y dot y. You can sit down and carry out a calculation of this because the dot product has the coordinates kind of separated from each other. If you carry out the integral, the one-dimensional case implies the higher dimensional case. Now, if you insert a positive scaling factor, the things are going to be slightly different. Instead of 1 over the square root of t, you get 1 over, let's say, t to the k halves. So if k is 1, you get 1 over the square root, but otherwise it's higher powers of the square root times e to the minus pi y dot y over t. Ugh, I'm running out of space here. What? You know what? Why don't I just make it smaller? Okay. E to the minus y dot y over t. Ah! Ah! Sorry, I lost the pi factor there. Okay, so here we go. All right. E to the minus pi. Anyway, it's the same. It looks the same. Okay. Okay. So in terms of the theta function that we were working with connected to the Riemann zeta function, the theta function was you were summing over the integers e to the minus pi n squared t. And so this is your summing over the integers, that second example. Right? So our second example here, we're summing that over the integers. And so by the Poisson summation formula, it would be the same as summing its Fourier transform over the integers. And so that's where we got the relation that theta of t is 1 over root t. 1 over root t, take that factor to the outside, times this at 1 over t. So you can rescale, or you can swap t with minus t. Theta of 1 over t is root t theta of t. And in higher dimensions, we could take, if theta of t was summing over all of z to the k, e to the minus pi, well, I guess we could say v dot v times t, then you're summing the example, our second example again. Oh my God, what did I just do? Sorry. Right, this example, here I'm summing it, and so by the Poisson summation formula, I'm just summing over z to the k, the Fourier transform 1 over t to the k over 2 times e to the minus pi v dot v over t. So we get 1 over t to the k halves theta of 1 over t. Okay, so it's a natural generalization. And if I swap t with minus t, I get theta of 1 over t is t to the k halves theta of t. So here we get very similar looking expressions in both dimensions. Okay, but just the power of t changes if the dimension goes above 1. All right, now, what we're really going to be interested in higher dimensions is to replace the ordinary dot product, which is a particular example of a positive definite quadratic form. So it's just straight sum of squares with a more general positive definite quadratic form. And so I'll just report to you what the answer is in that case. So if you have a quadratic form, we know we can always write it as x dot ax, where a is, sorry, I underlined the wrong thing, where a is a symmetric matrix. If this is positive definite, then if we set f of x to be e to the minus pi q of xt, where t is a positive number, then what happens is the Fourier transform turns out to be 1 over t to the k halves. Then we get a factor of the determinant of that matrix, or rather the square root of the determinant of that matrix. And then you can get e to the minus pi. Instead of q of x, we're going to get another quadratic form. I'll write q star of x times 1 over t, where, oh, I'm sorry, I should have my Fourier transform variable was y, not x. And so this new quadratic form is just obtained by replacing A with its inverse. Okay, if x dot ax is a positive definite quadratic form for a symmetric matrix A, the inverse of A is also symmetric, and this gives you a second quadratic form. And so note, by the way, of course, if you iterate this operation twice, you go back to the original quadratic form because you just inverted A twice. So, so that's a new, right? Here's my function with a general positive definite quadratic form and a positive scaling factor. And there's the Fourier transform. And so we can make this calculation. I'll present a discussion of it, excuse me, in the notes. And so, so if I take, what was the theta function of the quadratic form? You were summing over z to the k of e to the minus pi times your quadratic form at those vectors times t. And so using the Poisson summation formula, you're going to get 1 over t to the k halves square root of the determinant times the theta function of a second quadratic form, q star of 1 over t. Where, again, if q is x dot ax, q star is y dot a inverse y. Okay? So for some quadratic forms, I mean, if A is equal to its own inverse, you're going to get the same theta function back. But in general, you're going to get a theta function of a second quadratic form. If the determinant of the matrix is 1, doesn't have to be the identity. If the determinant of the matrix is 1, you don't see that determinant factor on the right side of this transformation formula. But typically, from Q, you get a Q star, and you can go back and forth. If you iterate it twice, you get back to where you started. All right, so the general story is we're connecting theta function of one quadratic form through Poisson's summation. Right, this comes from, this is a very analytic equation. This is using Poisson's summation on Euclidean space in k dimensions. You're going to get a connection between a theta function of one quadratic form at t and a second associated quadratic form at 1 over t, up to a certain definite scaling factor. Right? So if the quadratic form is just a sum of squares, if Q is a sum of squares, A is the identity matrix, Q star equals Q, and you get back to the thing I have in green up above. So maybe I'll color this one in green also. Right? For a general quadratic form, the relation, the value at t and 1 over t are linking two different quadratic forms, but if it's the same quadratic form, then if I replace t with 1 over t, excuse me, if I replace t with 1 over t, then on the right side, the denominator gets t to the k halves in the numerator, and I get the value at t. And so now I'll uncolor this green business, and I'll instead color this one in green instead. So this is the analog of, for a general positive definite quadratic form, of what we had up above for the straight sum of squares up there in the right in green. That was the sum of squares quadratic form. And the general story, it looks very similar, except you have a possible denominator. You see it if the determinant is not 1, and you have a second quadratic form on the right side. Typically, but of course in special cases like a sum of squares, it's its own dual or its own associated quadratic form. So anyway. Okay, so are there any questions about what's thing here? So it all looks very similar to what we had before. You get a few new wrinkles come up. Quadratic forms in more than one dimension are more complicated than in just one dimension. Okay, so we're going to want to use this to get the analytic continuation of the zeta function of the quadratic form. So let me first, though, look at the simplest case. So we want to apply this to get an analytic continuation. I really should say meromorphic continuation. An analytic continuation of the zeta function of the quadratic form. Let me remind you, you just sum 1 over qv to the s. So this is for the real part of s, let's just say large enough. Okay, I don't want to be fussy today about how far out you have to go. I mean, it should be for the real part of s bigger than k over 2, but let's not worry about that detail right now. So there's your zeta function in the quadratic form. I want to get an analytic continuation of this to all of c. It initially only converges on the right half plane, and it's going to have poles at with a pole at k over 2. So in the binary case, binary quadratic form, for instance, if I took x squared plus, I don't know, say 5y squared, this has a continuation to the complex plane with a pole at s equal 1. Okay, this is the case in k equals 2. So it looks like the Riemann zeta function, which has a pole just at s equals 1. Right? So how are we going to do this? So first, I want to present what happens in the one-dimensional case, because that's connected to something that we already know that we did last time. So let's. So this was the case k equals 2. K equals 2. So k halves equals 1. But let's just take a look at the one-dimensional case, q of x equals x squared. Okay, the silliest quadratic, the most basic quadratic form, just in one dimension. So then the zeta function of q is you want to sum, we're in one dimension, so we're going to sum over the integers that are not 0. Did I leave that out here? How come nobody corrected me? You're waiting to see if I would notice. Yeah. So of course, you can't sum over at the term 0 is not really there, because the denominator then q of 0 is 0, so we don't include that. That's the only term we're omitting. So if we sum 1 over q of n, then we're summing over the integers that aren't 0 of 1 over n squared. And so you can turn that into a sum over positive integers of 1 over n squared, but now minus n and n contribute equally. So what happened to my variable? I raised to the power s, I raised to the power s, I raised to the 2s, and this is twice the Riemann zeta function at 2s. So that's what the zeta function of x squared looks like. And we already know, we saw last time, that for the completed Riemann zeta function, pi to the minus s over 2 gamma of s over 2 times zeta of s, we have, it extends to the whole complex plane from its initial definition to the right of 1, and we have the equation z of s equals z of 1 minus s. And so if I want to get something nice involving zeta of 2s, if you just stare at this completed zeta function, why don't we just double everything? Okay? So let's set, I'll call it big F of s is z of 2s. And so if you just double s everywhere, you get pi to the minus s, gamma of s, zeta of 2s. Okay, the completed zeta, the original zeta function had an extra factor of 2. That's not really going to affect anything, but if you insist that I put it there, I can just put a 1/2 out front. It doesn't really matter. Gamma of s, and now doubling it finally gives me zeta q of s, all right? And so the original equation, z of s is z of 1 minus s. I want to replace s with 2s, so, whoops, sorry about that. So this thing, if I replace s with 2s everywhere, I get z of 2s is z of 1 minus 2s. But I'd really prefer to have on both sides z of twice something. So how can I pull out a factor of 2? You're good at algebra, right? Fill in the blank. Huh? Yeah, 1/2 minus s. Okay, so what we get then is f of s is f of 1/2 minus s. All right. Notice in an equation like this, like if you doubled both sides, it's the same kind of equation if you tripled both sides. So that extra factor of 2, they'll have 2 zeta of 2s. The 2 on the outside is really a very kind of irrelevant factor. The 2 on the inside, of course, that changes things a bit. But you shouldn't consider the 2 on the outside to really be a very serious factor there. But in any case, so there is our completed, in this language of quadratic forms, the zeta function of x squared has a completed version. You multiply by pi to the minus s times gamma of s, and then with or without an extra factor of 1/2, and then you get that function extends to the complex plane, its value at s, and 1 minus s is the same. Okay? So what we're going to find happens, and I think I presented this with some mistakes in the first lecture. So it turns out that for the general case, for a general positive definite quadratic form in k variables, we're going to define the completed zeta function to be pi to the minus s times gamma of s times the zeta function of s for a real part of s large enough. So this is going to has an analytic continuation to C. With poles, simple poles, at 2 numbers, 0 and k halves. But you see the gamma function factor on the right side? The gamma function has a pole at 0, and so the thing on the left also has a pole at 0, and they're both simple. Then the ratio, when you solve for zeta of s, the pole is going to cancel. So the zeta function, zeta q of s, is lowercase zeta q of s on the right side is not going to have a pole at 0. All that will survive is the pole at k over 2. So there's this distinction when you add on some powers of pi and gamma factors to get some nice functional equation that I have not written down here. This completed version could have a pole where the original Dirichlet series does not, and it's because of something like this, where the gamma function also has a pole, and so the ratio cancels out. So moreover, we're going to have the equation zq of s will be 1 over the square root of d times zq star of k halves minus s. Let me make sure that I'm recording this correctly. Yes, right. So the functional equation is going to link the zeta function at q and the completed zeta function at that associated quadratic form, the one defined using the inverse matrix to the symmetric matrix that defined the first quadratic form. And what the heck is d? Where d is the determinant of that matrix defining the quadratic form. So a certain positive number, right? Q of x was x dot ax. Right? So if you had a sum of squares quadratic form, d is just going to be 1, and you wouldn't even notice it. So if q of x is x dot x, we're going to have d equals 1, q equals q star, and d equals 1. So you're not even going to notice. It's just going to say that zq of s is zq of k halves minus s. You're going to relate a function to s and that same exact function at k halves minus s. Okay, because q will equal q star because the sum of squares quadratic form has the matrix associated to it, which is just the identity, so it's its own inverse. So anyway, okay. All right, so this is our goal, is to get that this product here, we're going to see it has poles, and especially we want to see this functional equation, where that comes from. All right? So the motivation for this is exactly in the case of the one-dimensional example of x squared. We saw that the natural thing to do is to multiply it by pi to the minus s gamma of s. And you might think in higher dimensions you have to do something more complicated, but it turns out that exactly that factor will treat all quadratic forms in any number of dimensions in the same way. That one factor will multiplying that times the zeta function of the quadratic form will have a nice functional equation, but we get this phenomenon that it relates two quadratic forms, the completed zeta function of two quadratic forms. And if anyone has studied Dirichlet-L functions, you see the same thing happening there, that the functional equation will relate the Dirichlet-L function at one character with the complex conjugate character, which may not, typically is not the original character unless it's real valued a quadratic character. Yeah? So this idea of the functional equation linking two associated objects that may not be the same is a pretty typical thing in this kind of story. Okay, so excuse me. So yeah, let's go ahead and proceed like we did yesterday. We're going to write pi to the minus s times gamma of s as an integral, and we're going to multiply it by the zeta function q as a Dirichlet series. We're going to put it on the inside, make some multiplicative changes of variable, swap the sum in the integral, and then we're going to see a theta function popping out. Okay, and so things will be very similar to what we saw last time. Okay, so this is our goal. All right. Okay. Okay. So the completed zeta function, we get pi to the minus s, gamma of s. Yes. Question. Yes.
So you said that like the functional equation relates the zq of s to zq star of this k over 2 minus s. So like if we want to, for example, let's say get a value of zq to the left of like the line k over 2 minus s.
Good luck with that. Yeah, I mean it's well, you're relating. It would be like if you wanted to know zq of, I don't know, minus 1/3, right, then you need to be able to calculate the other zeta function at k halves plus 1/3.
Right. So you need to kind of know both zeta functions if you want to really know what the.
If you want to, yes, if you wanted to use this equation to calculate values of the left side at highly negative numbers, you definitely would need to know. The right side at highly positive numbers. Yes, that's a good point. Yes, so you have to keep both things in mind, which you may not have expected at first, because we just zeta q of s. It doesn't suggest that it needs q star, but it just kind of pops out. Yeah, I mean the same thing which happens with Dirichlet-L functions. If you've seen those, that right, you want to know value at negative numbers, you have to use the conjugate character at positive the complex conjugate character at positive numbers. Okay, so. Yeah, so let's write this thing out here. So let's see. The gamma function is, let's just say we're going for a real part large enough that the Dirichlet series converges. The gamma function integral x to the minus s e to the minus x dx over x times zeta q. If we bring the pi inside the integral, we can put it downstairs, and we're going to make a multiplicative change of variables. Let's see. Let's of course. Oops. Let's of course let y be x over pi. Multiplicative change of variables will not change dx over x. dy over y is dx over x. The range of integration is still from 0 to infinity. Now you get y to the x, e to the minus, let's see, x is pi y, and dx over x is dy over y. All right. So now I want to bring, let's see, I guess we can write, maybe all right, this is a sum over zk, not 0, 1 over qv to the s. And so I'm going to take this entire expression and put it on the inside. And so if I bring that whole expression to the inside, then, and bring that 1 over qv to the s inside the integral, it's just a number. It's math. Everything's just numbers. Okay. So now we're going to do another multiplicative change of variables. We're going to let, I guess we'll let u be y over, for each, in the integral, each integral here, the sum of integrals depends on v, so defining u this way, so dy over y is du over u. And we're going to see that the completed zeta function is going to get a sum over z to the k over non-zero terms of the integral. So when you make your change of variables, maybe I should have written this as y over this all to the s. That looks better. And so y over that, I'm going to get u to the s, whoops, u to the s, e to the minus, now pi y. Y is q of vu. So pi q of vu, and dy over y is du over u. So now we have a sum of integrals, and everything converges nicely enough that it is valid to swap the order of summation and integration. And so now we're summing on the inside a sum over non-zero elements of the standard lattice. And now in this sum, it's a sum over v. The u to the s doesn't even depend on that. It's just e to the minus pi q of v u. So v is a vector, u is a real variable. That's positive. Okay? So we just swap the order of sum and integral. That can be justified. And then we have this. Now the thing on the inside that is nearly the theta function. Is it the theta function? What would the term in the sum be when v is 0? If I put the v equals 0 term back in, what's the term when v is 0? 1. So therefore, I'm going to rewrite this as theta q of u minus 1. Okay, so taking off the constant term. So just for a reality check, right, this resembles the completed zeta function. It was an integral theta of u minus 1 over 2, u to the s halves du over u, where theta was the sum over all integers of e to the minus pi n squared u. Okay, so it looks very similar, right? So here's it's probably worth remembering. We've completed zeta function written as an integral involving the theta function. So when I introduced the theta function and the zeta function on the first day, they were just kind of two separate things, but in fact they're very closely related, right? Because this guy here, remember, this is pi to the minus s, gamma of s, zeta q of s. And so here you have this equation. We can even highlight that one, right? So the zeta function of the quadratic form is expressible as an integral in terms of the theta function of the quadratic form. So it's what I call the integral representation for the zeta function of q. And so just like last time, we're going to split the integral because there's an equation. Well, it doesn't connect theta q of u and theta q of 1 over u. We have theta q of u and theta q star of 1 over u. Where was that? Where was that? There it is. Okay, so we have an equation connecting the theta functions of the quadratic form q and q star with their values at t and 1 over t. And so what we're going to do here is we're going to take this equation, and now we're going to split the integral into a sum of two integrals from 0 to 1 and 1 to infinity. So let's see. We'll first go from 0 to 1. It's just going to be the same exact thing. We're just splitting it into two terms so I can apply that transformation formula. And then 1 to infinity of exactly the same stuff. U to the s du over u. And so now the key thing here, just like I said last time, this second integral is starting at 1. The subtlety of these integrals is the behavior near u equals 0. When you have a lower bound that's positive, although initially these integrals were only defined for real part large, that second integral, this actually converges for all complex numbers and is analytic. This is an entire function. The subtlety is the integral when you're integrating close to 0. So when I split up the integral, now that first part, the second part is actually convergent and analytic for all s. The first part, of course, I'm going to want to do a change of variables. So I want to change u to 1 over u. So that 0 becomes infinity, 1 becomes 1. So if I change u to 1 over u, u to the s becomes u to the minus s. And when you swap u with 1 over u, du over u becomes minus du over u. Remember I said yesterday, d of u to the n over u to the n, you can bring out the n. It's n du over u. So take n to be minus 1. And so now I'm going to keep the same integral. Ooh, I can copy, paste. Ooh, it didn't fit. Well, okay, we can bring the whole thing down. All right. Ding. Okay. So here we have an expression, and now the this. You know what? I'll just do it again. Oh, I guess I can't. And so that minus sign with the reversed integration, I can of course put it back in correct order. And now it's time to use that relation connecting theta q of 1 over u with theta q star at u. So we have the same integral as the second term, u to the s du over u. All right. So now both integrals are from 1 to infinity. And this thing here, what is this as a function of u? If we go back up to, where were we? Right there. So theta q of 1 over something is that thing to the k halves over the square root of the determinant of the matrix defined in the quadratic form times theta of q star at u. So here we have theta q of 1 over u. So this is u to the k halves over the square root of the determinant of the matrix defining q times theta q star of u. And we were calling the determinant of the matrix A, we were calling that D. All right. So now we're just going to put that in there. So now we're integrating from 1 to infinity, e to the k halves times theta q star. So the second quadratic form is making an appearance, and everything else is unchanged. So what I would like to have, I would prefer in the first integral that where I see theta, I really would like to see theta minus 1. Remember we had this kind of business yesterday with the Riemann zeta function. We had a factor of square root of u. Right? When k is 1, that's saying u to the 1/2 times theta of u. Right? For a one-dimensional or sum of squares quadratic form, q and q star would be the same. It would look very similar to what we had last time. D, the determinant, would be 1. For the sum of squares quadratic form, the matrix A is the identity. So this would be very similar to what we had last time. So I really would prefer to have where I see, because I want to get rid of the constant term. So what I'll do is I'm going to write theta q star of u. I'm going to subtract 1 and add 1. That hasn't changed anything. And now put the minus 1 there. That it really is, got to look at it, see, it really is the same thing. Okay. So now we want to keep theta minus 1 together. Now that I've subtracted the constant term, that's unchanged. Okay, so now so here, this thing, we want to keep this together, just like we want to keep this together. Because you're taking away the constant term, which makes the first term, when you wrote out the theta function as a series, who knows what the smallest positive value of the quadratic form is, but whatever it is, it'll be a negative exponential. So this thing is going to decay exponentially. So that's very nice when the integral is going out to infinity and it's staying away from 0. So we can break up this first integral into 2 parts. So that looks correct. I'm going to distribute everything else. And now I'm going to have the integral of what's left in the first integral, u to the k halves over square root of d minus 1 u to the minus s du over u. Can anybody else vouch that that's correct? Anybody else say, yeah, that looks right? Do the math. Right, when we have, this is a factor I'm multiplying by the 1, and then I have just this old minus 1. So that minus 1, and they're both being multiplied by u to the minus s. So there's the minus 1, and there's the u to the k halves over root d times 1. Anybody agree? Huh? Looks good. All right. Yeah. Okay. I was freaking out about an hour and a half ago because I had introduced an incorrect numerical factor. I was like, oh my God, I have to give this talk in an hour and a half. What am I going to do? And everything works out. All right. Okay. All right. So, boy, this is a mess. So here, look, I have 2 terms that look the same. And also what I have here, what happens if I use pink? That looks okay. Okay. So those are 2 powers u. I can combine those together to get a u to the k halves minus s. Ooh, that looks good. Okay. So what I'm going to do here is I'm going to emphasize the theta q star u minus 1 first, combine the u terms together. I did not forget about the denominator. Then I'm going to bring the third integral closer to here. And now I'm going to put the middle integral at the end. And what I would like to do, I have a difference of terms. So the first thing, I have a u to the minus s, so I want to put the s downstairs. If I have 1 over u to the s, the first part, I'm going to want to subtract k halves, but then also add 1 because I do have the du over u. So the first term, that's the correct power of u, and I also need a square root of d. And then I want to subtract du over u to the s plus 1. Because I have a u to the minus s divided by u is u to the s plus 1. And so the second term is just subtracting that off. Right? So this term here, I'm subtracting, that's what that piece is, and then the first part is that's what that piece is. Right? Does that look okay? Yeah? Yes? Yes? Okay. Now these last 2 integrals we can actually be able to calculate, but let's put the first 2 things together. So remember, this is all just the completed zeta function, right? Up at the top, zq of s. So, and I really would prefer to put the q before the q star. So let's put the second integrand first. So this thing times u to the s plus this thing with q star over root d times u to the k halves minus s, and everything times du over u. And then we're going to have two more terms. Those two more terms, that's the two more terms, that's the combination of those two things. So I'll just put them on top of each other. All right, so let's calculate those, because those are just integrating from 1 to infinity of a reciprocal power. Right? As long as your exponent is above 1, if you integrate it from 1 to infinity of du over u to the z, you're going to get 1 over z minus 1. That's just a calculation. So now we can take the we can take the first integral. I don't know how you're doing this with a pencil. All right. And then the other terms, which gonna, all it is 1 over the exponent minus 1. So the first thing is 1 over the exponent, s minus k halves plus 1, take away 1. So s minus k halves times 1 over root d. I agree. And the next term is subtracting 1 over s, because the exponent is s plus 1. So that's this bit evaluates to 1 over s, and the other bit, oh my God, what did I just do? The other bit is that, okay? And so now we've just, look at that. This whole thing here, because I'm integrating it from 1 to infinity, this is an entire function. Because the lower bound is positive, you're staying away from 0. The theta function decays very rapidly at infinity. It's kind of a subtle thing close to 0, but we move the integration away from 0. And this thing, here I have a pole at k over 2, and here I have a pole at s equals 0. Right? So, and so what we see then, if we move this up to the top, is this equation shows us, okay, so this right side gives an analytic continuation of the zeta function to the whole complex plane with poles that are both simple only at 0 and k over 2, where the residue at s equals 0, what's the residue at s equals 0? It's a minus 1 over s, so the residue is minus 1. And the residue at k halves, we have 1 over s minus k halves, and the numerator, or the coefficient, is 1 over the square root of d. D was the determinant of the matrix that defined the quadratic form. Okay, and now what about the functional equation? So what happens? So first of all, I have k halves minus s in the exponent in the integral, but I have s minus k halves in the term. So let me negate that. Let me negate that. So I'm going to rewrite this. ZQ of s. I'm not going to rewrite it. I'm just going to cut and paste it. Okay. So we get this thing. And then the other term, I'm going to subtract 1 over k halves minus s. So both polar terms, I'm going to subtract 1 over k halves minus s, because minus 1 over k halves minus s is 1 over s minus k halves, and then I'm going to subtract 1 over s. Okay? And so now what happens is, so this is the same exact formula as before, and now I'm going to replace q with q star, everywhere. And when I do that, recall if I take Q star and I star it again, I get back to where I started. And so if you do that, then what you're going to find happening is, let me just, where was this? Yeah, so you're going to find that Z Q star of S will be root D times ZQ of K halves minus S. You have to do a little bit of algebra here with you're mucking around with the factor of the square root of D, or Z Q star. If you just replace S with K halves minus S, you get that. So anyway, you can solve for ZQ of S. You get 1 over root D. Oh, you should be careful here that when you replace Q with Q star, you're basically replacing the matrix A with its inverse. So the D, the factor of D, gets changed into 1 over D because I was the determinant of that matrix. Okay, so you have to do a little bit of algebra there. Anyway, so there we get the functional equation. And so since I have about, I have minus 1 minute left. So the last thing I'll just say is that in 1935, it was shown that, let's say, just as a concrete example, for Q equal to x squared plus 5y squared, that the zeta function has infinitely many zeros on the line real part equals 1/2, and infinitely many zeros on the half plane to the right, and even beyond real part equals 1. This is very unusual, but let me remind you, this doesn't have an Euler product. And so the fact that this breaks the Riemann hypothesis pretty badly is not really a counterexample. It's more of a warning that just because something resembles the zeta function doesn't mean it should satisfy the Riemann hypothesis. So this was proved by 2 British mathematicians named Potter and Titchmarsh. Now, what do you suppose Potter's first name was? Harry. His first name was Harold. Yeah, Harold. Yeah, Harold Potter. Yes. So Google Harold Potter zeta function. You can find he was working on math back in the 1930s. Anyway, and so very recently, Rezviakova, a couple of years ago, this will be the last thing I say, Rezviakova showed a couple of years ago, it looks like the theorem was by 1935. Potter and Titchmarsh. Rezviakova showed that for all binary quadratic forms, for k equals 2, any positive definite binary quadratic form, the zeta function for q has a positive proportion of zeros on the line 1/2. And this is interesting because this does not satisfy, this is known, like in particular examples like the x squared plus 5y squared, I mean, it's known not to satisfy the Riemann hypothesis, yet apparently it has a positive proportion of zeros on the critical line. So you will find in the literature as evidence towards the Riemann hypothesis, people will say, oh, the Riemann zeta function has like at least 1/3 or at least 40% of the zeros counted by their height are on the line real part equals 1/2. That's like towards the Riemann hypothesis. But the fact that things that don't satisfy the Riemann hypothesis also have that calls into question the value of any of these positive proportion of zeros on the critical line as being any evidence at all for the Riemann hypothesis in the cases where you expect it to hold. So anyway, yeah. All right, I'll stop there for today.